Hello and welcome back. In gradient descent, we have seen the memory issue. When it is making one step or trying to calculate the next theta, it is using the whole data set. So that's an issue. When you have huge volume of trained data, you cannot actually perform or use the solver to find out best thetas. So stochastic gradient descent is an algorithm which can solve the problem. In stochastic gradient descent, we'll take one record at a time to calculate the next theta. That's the simple thing. Same gradient descent algorithm. Instead of taking whole data, we'll take one record at a time. If you look at this code block, we can understand it clearly. So I have taken x and y into the input variables into x and the output variables into y. And then we have epochs, n epochs, that is 5 epochs we are doing, or iterations. And in the gradient descent, we directly calculated the gradients using the total data set. But in here, we have taken the m iterations inside each epoch. And we are choosing that, that index, the first index, right, m number of iterations. That means if there are m number of records, we will do m number of iterations in each epoch. So here I have chosen I, maybe it is 0 first. And then I will go in and say rand int of 0. It will generate one number. And using that random number, I am picking a record from x and y. That is xi and yi. Suppose that the random index picked is 50. Or in this particular data set, we have got only 25 records, right? So maybe it is 15. Right? The 15th record x and 15th record y we took and then calculated the gradient. So using this formula, we calculate theta transpose x here. That is, there is no transpose there because of the x structure. And we multiplied these two. That is the logit, and then that's a prediction minus yi, and multiplied with x, and then calculated gradient, and then we subtracted this gradient from theta by multiplying with eta, which is nothing but learning rate. But here it is learning schedule. We'll talk about learning schedule in a moment. But if you look at this clearly, it is using one record at a time to calculate the next gradient. By taking one record at a time and doing n number of epochs, right, the algorithm will reach to the global minimal error place, or the best theta place it will find. Okay, so with this algorithm, it makes it is faster because less number of records, one record only it is actually processing at a time when compared with the gradient descent. The second thing is huge training data also it can handle. Even if you have 1 billion records, we'll take one record at a time and process it. So that is stochastic gradient descent and how it is solving the memory issue. So if you use stochastic gradient descent, there will not be a dummy variable trap as well as memory issue and processing issue also. So in general, in deep learning also, we'll use stochastic gradient descent or mini batch gradient descent. Mini batch gradient descent is a little bit advanced version or kind of modified version of stochastic gradient descent, where you will take a batch of records. Instead of passing one record at a time, you will take a batch of records, and maybe 8 records at a time to calculate one gradient, maybe 16 records at a time to calculate one gradient descent. Why batch gradient descent or why mini batch gradient descent? Because when you use stochastic gradient descent, the theta, the gradient calculated may be a little bit not so appropriate, because one records x and y may be having a different kind of pattern, and another records x and y may be having different kind of pattern. We are trying to understand pattern by looking at x and y both, right? So when you use one record at a time, the understanding may be a little confusing. If you use whole data and try to understand the pattern, it is going to be more solid because you are trying to solve all equations at once. But here in stochastic gradient descent, you are trying to use one record at a time. Because of this nature, because of this particular behavior of the algorithm, the cost function is going to be little jumpy, or it is not going to be perfectly convex. The cost function is not perfectly convex. It will have highs and lows and jumpy nature. We'll see that in a moment. Before we go there, To reduce the jumpy nature, the solution is that we need to use learning schedule. Okay, so the learning schedule will actually reduce the alpha value, the eta value. With each iteration, it will reduce a little bit. To create that scenario, the formula, look at this, t0 divided by t plus t1. The t is a calculated value. With each iteration, we are calculating the t value and passing it to the method. And t1 is a big number. See this, t0 is 5 and t1 is a big number, right? It is a 600,000. So with each iteration, the 600,000 will increase, right? The 600,000 value will get added. The t1 value will get added with t. That means it's going to increase a little bit. When denominator increases, the return value actually reduces, or the learning rate reduces with each iteration in stochastic gradient descent. To reduce the jumpy nature of the cost function, we will use this learning schedule formula. Okay, so as a whole, stochastic gradient descent actually works on huge data, and then it works faster because it is working with only one record at a time, and then huge volume of data it can work with. Let us jump in and try to look at the accuracy it got in number of iterations. So if you look at this, right, we have epoch 1 to epoch 5. By epoch 5, it actually achieved 334. In our gradient descent, we achieved 333 in 70 iterations or 60 iterations in 1500 calculations, 1500 matrix manipulations, because we are using whole data to calculate next theta. But here we are using one record at a time, right? So we did 5 epochs. That means in each epoch, in this particular data set, we have got 25 records. So we are doing only 125 math manipulations. In 125 math manipulations, we have got 334. That means now one number more than the accuracy we have got on the batch gradient descent. But the amount of processing power you used is very less. 125 compared to 1500 is very less, right? So when you look at stochastic gradient descent, it always will not reach to the global minimal theta, but it actually jumps around that minimal global theta. When you look at that stochastic, that parabolic curve of the theta and j of theta, batch gradient descent definitely reaches to the global minimum, but the stochastic gradient descent reaches here and just jumps around. It will not stay in a single place because of the one record at a time processing thing. One record may give one kind of a pattern, and another record may give another kind of a pattern. Because of these little bit minute pattern changes, the theta will jump around the global minima. It may not stay at a single point. Even though it is not staying at a single point, stochastic gradient descent is best, because in 125 math calculations we have got the almost best accuracy. That means almost best theta we were able to find. Okay, so that's about the stochastic gradient descent. We'll understand a little more about why this equation is gradient, and consolidating the gradient descent algorithm. We'll do it in next video. Thank you.